In this video, we're just going to go over the periodic trends that you observe on this wonderful periodic table. So the first one we're going to look at here is atomic radius. And that's what everything else is built around. Because the bigger atoms are, the weaker they hold onto their electrons, because their nucleus is far away from their electrons. So over here, down at the bottom left, we've got our biggest elements, and they hold onto their electrons very weakly. And up over here, you get over to the ones that really hold onto them strongly up in this corner. So the smaller they are, the harder they hold onto their electrons. And the reason for that is, if you draw an atom, if you have a large, that is completely not look like an atom, but the nucleus in the middle where it's positive, and if you have an electron out there where it's negative, the further away it is, the weaker the attraction based on Coulomb's law, because the attraction drops off with the square of the distance. Now, related to that is ionization energy. So ionization energy is the energy required to remove an electron from a neutral element. And you can see that these are really weak, green representing really weak. And over here it's really, really high, meaning there's a high energy associated or required to remove that first electron. Again, completely related to the size, but inversely related to the size. Then, similarly, electronegativity represents the strength an atom has when attracting electrons in a bond. So you can see that the really weak ones are over here, and the really strong ones are up here. You might notice that some of the noble gases are left out. The reason for that is they don't form bonds, so they can't have any strength when attracting electrons in a bond if they don't bond. Fluorine can't help itself, it's so attractive, and it has an electronegativity of almost 4. The bigger the difference in the electronegativities between two atoms bonding, the more ionic character it has. The closer together they are, the more covalent character they have. And what that means is when you have an ionic bond, one atom steals an electron from the other. The higher electronegativity will steal the electron and become negative, and the weaker one will lose the electron and become positive. So the closer together their electronegativities are, the less that's likely to occur. And we say that that would be more covalent character. The further apart they are, the more ionic character, because more it's a stealing rather than a sharing. So additionally, we'll look at electron affinity, which is the energy change associated with the addition of an electron to a neutral gaseous atom. So there's it's not like a straightforward trend, but there's a couple things I just want to point out. That if you look at the electron affinities for the ones in yellow, those are not bad. Notice that the ones that are green, they have an electron affinity of 0, meaning it's not going to happen. These elements contain a completed S subshell, and therefore to add an electron, it would have to go to a P subshell, which is further away. Not highly probable. These elements right here, they've completed their D subshell. To add another electron, you'd have to start a P subshell, which is higher in energy. Not going to happen. And you're not going to add an electron to a noble gas because, well, then it would have to start a whole new shell. So you're putting it to a much higher potential energy. So those are the periodic trends that we really care about at this point in time. And for metals, the bigger they are, the weaker they hold their electrons, the more reactive they are. For nonmetals, the smaller they are, the stronger they hold their electrons, the more reactive they are. So they're exactly the opposite of each other.